So first off today, I want to finish off material from lecture 7. And the main thing that we're going to be worrying about, well, two things actually. So in the classical case, we discussed like two different ways of thinking about errors. So in one case, we've said, oh, there's this finite set of errors, like single bit flips, and we want to be able to correct those. The other case, we said, just something that can happen to my stuff that goes over the channel, like a bit can get flipped, and I want to be able to correct with high probability, right? And those were related. Okay, we need to do the same thing in the quantum context. So far we've been talking about, so far I just gave you like examples of codes. We haven't discussed them super systematically, but we kind of fiddled around with them and got a sense of them. And we noticed that, for instance, in this 9-qubit code, we could correct single qubit X and Z errors, and a little bit more than that, but at least that, right? We want to go from, we have codes that correct single qubit X and Z errors or something like that, to I just have some general noise that happens to my qubits. How much does my error correction sort of improve the situation? How much does it reduce this noise? Okay, and then the other thing we're going to do in sort of discussing codes a bit more systematically is we're going to have a procedure or a set of conditions such that if I give you an encoding, like I say, I take my qubit and I do this to it, then we want to just be able to tell what are the set of correctable errors. Or at least if I give you a set of errors, there should be some simple computation you can do to check if they're correctable or not, right? And we don't really know how to do that. Right now, we just kind of ad hoc, case by case, looked at examples. Okay, so let's get started with the first thing. So how do we combat general noise? So the first thing I want to do is move from, let me write down what I mean by general noise first. So for instance, or in particular, we can think about a channel, it's a really curly A, that acts on my physical space, right? And the setting we're interested in is just where I don't know all that much about the channel except that it's close to the identity. Okay. Yeah. And okay, so that's the most general thing we'd like to be able to address. We're gonna think about something a little bit more restrictive. We're gonna say that in particular, we'll assume that the noise channel like acts independently on each of my physical qubits. Okay. You can move beyond that as well. But that's the case we're going to address. And you can see that this is kind of physically motivated. So for example, if I was in the setting where I'm trying to communicate, taking each qubit and separately sending it over the channel, it would make sense if the noise on each qubit is independent, right? Writing this down is just like the quantum analog of saying that before, in the classical case, each bit I send over has some probability p of getting flipped, and those probabilities weren't like correlated with one another. If the first bit gets flipped, it doesn't mean the next one is less likely to get flipped or something. It's independent noise. So this is independent noise in the quantum case. Okay, so we want to know like how can I combat this kind of noise, right? Okay, the first step towards doing that is going to be that we want to move from correcting Pauli errors to correcting arbitrary errors. Okay. But we're going to restrict still to some subset of the qubits. So we say, okay, I can correct Pauli errors on t qubits, where t is maybe less than n, and I'm encoding into n qubits. The claim here is that actually means that I can correct arbitrary errors on those that same set of t qubits. Okay, so let's prove that. The proof isn't too hard. So the assumption is that we have some decoder channel that has this property, right? I have my state in the physical space. It's been acted on by some Pauli error. And the decoder, by assumption, gets me back to the same state. Well, okay, actually, I've phrased things in two different ways here. So before I was defining the decoder as taking you back to the logical space, right? Like taking you back to where this came from. Yeah, in the logical space. The code correcting this error also means that there's a map here. So I could just use the decoder that takes me back to the corresponding state in the logical space, and then use the encoding again and get back to the same code word, the same state in the physical space. But I'm going to think about it this way. Good. Okay. And then I'm going to use that. Actually, any linear operator can be written as a sum over the Pauli operators. Okay. I made a statement like this, similar to this before. I said all the density matrices can be written as a sum over the Paulis. For density matrices, these coefficients are real, right? For arbitrary, just 2 by 2 matrices, these are complex, right? Okay, and that's how I get like non-Hermitian operators here. Okay, so I have that. And then I also want to think about the isometric extension of this channel, right? So we know that I can always view this channel as coming from some unitary that acts on, you know, this input plus some ancilla and then traces out the ancilla. So let's call that isometry like non-curly D. And it should have, okay, and I'll think about that isometry acting on like E, this error. Psi, and then there's some ancilla now. Okay. I'll decompose E this way. I'll use linearity to pull this sum outside of the, or before D. So this looks like sum over ij, alpha ij, d xi cj psi 0. Okay, and then I know how this thing acts, right? So as a channel, when I just view this, it just gives me psi back. Now there's this ancilla, and I'm not tracing it out anymore, like I would here. So it can end up, you know, in some arbitrary state, which could in general depend on ij. So this is going to look, let me move here. Woof. We're inside of Zoom. Okay, so D like corrects this error, right? So it always has to put psi back to psi. And then it can, you know, dump some other stuff, some other information onto the ancilla system, which could have depended on ij.
Wait, I thought curly D got rid of the error. This D just wait, yeah, this D did just trace out the ancilla.
Okay, so I kind of did two things at once, so maybe that's confusing. But so this D, the curly D acts like this, right? And then I take the isometric extension of that. That's non-curly D. Maybe I should make it even less curly. And so from this, I see that the way non-curly D needs to act is like this, right? Because now if I do this and then trace out the ancilla, it's supposed to act like this channel. So it must take this form where the first system's left in the state psi, right? And then I'm just using that like inside the sum. Yeah, on each term by linearity. Okay, and then that's good because this side didn't depend on ij, right? So this is also just psi sum over ij, alpha ij, by ij. So this is psi, like some phi that depends in some way on which error I had. Right? Okay, so then that also means that like if I, well, okay, so we can see that now the error channel, which is just doing this and then tracing out the ancilla, would correct the arbitrary error and not just the XD errors. Okay, does that make sense? Okay, so that's good, right? We've somehow made a lot of progress here, right? Because it's like we just had to think about correcting, you know, three things: identity X, Z, XZ, Pauli operators, and then we know that we've corrected, you know, this big continuous set of errors. And naively, it seems hard, like if I, you know, if I can rotate my qubit by some arbitrary angle, it seems hard to correct that because there's so many different kinds of errors you could have. You could rotate by any angle. But it's saying that if I just get it to work on the Paulis, then I'm okay. Yeah.
So when you expand the... Oh, never mind.
You answered your own question. Great. Okay, so that's, yeah, that's progress.
Alex?
Yep.
Why did we need to add the ancilla? Like, why couldn't we have done this just like, you know, doing this whole thing with just the curly D?
You probably can. It's just messier. I mean, there's two sums, for example. Oh yeah. Actually, because you would get these like cross terms. So here, you know, like by having a particular Pauli error, it means you have like Pauli here and then the same Pauli there. If you directly try to use this, so you wrote this down, but with like E, and then stuck in the sums for E, expanded in terms of Paulis, you're going to have like different Paulis on either side. And then we don't initially, like a priori, have a promise as to how the recovery channel, the decoding channel is going to work on those terms.
So curly D acts on density matrices, but uncurly D acts on pure states?
Yes.
Okay,
Yeah.
thanks.
Yeah, so somehow it got us unconfused about these cross terms to go to the purified picture. Okay, so the next step is we have another theorem. I'm not going to prove this one. It's proven in the notes. It's kind of lengthy. Or the proof is kind of lengthy. So we're going to consider our like IID noise kind of channel. So I have all these channels. They act separately on each qubit. And we're going to assume that each of the terms in here, each of these factors, is close in some sense to the identity. And the amount of closeness that we need looks like this. N minus T minus 1. Okay. And then like A is going to act on the code words. So I feel like I keep using this, but maybe I haven't actually said what it means. So The code words are just the images of the logical space in the encoding. So I take some state in my logical space, I map it through this isometry into the physical space, and the states that I get there, I just call code words. Okay. Okay, so A acts on these code words. Of a code that corrects arbitrary t qubit errors. Then okay, so it's kind of a crazy looking thing, but let's break this down. So this is quantifying how well my my code corrects this error, right? It's saying I do the encoding, I have the error, I try and recover. How close was all that to just doing nothing, right? If my code is working perfectly, it's fixing all the noise, then this should be 0. This diamond norm should be 0. And this is claiming that somehow it's small in a certain sense, okay? And in particular, if my code corrects arbitrary errors on t qubits, and t is sort of big, it's pushing this this leftover noise after I've tried to correct it down to 0 as t gets big. Yeah.
Is n the number of qubits in this?
Sorry, yeah, n is the overall number of qubits in the physical space. Yeah. Okay. So this is the quantum analog. So last lecture I discussed. We said, okay, we have this IID noise for our classical channel, right? And we said that if we correct like low weight errors, or if we can correct errors up to a certain weight, and that weight is like larger than the expected number of errors, right? Then the only errors I don't correct are the ones like off on that tail of the Gaussian or of the binomial distribution, right? So the high weight ones are unlikely, and I correct all the low weight ones, and then typically I do well. I correct my noise. Okay. So this is saying a similar statement. It's saying if I can correct errors up to a certain weight, like acting on t qubits, then that's sort of good enough to correct small IID noise on lots of qubits. Okay. And the way that you prove this is very similar to the classical case. Again, it's like somehow most of the probability in some sense of what kind of errors occur are in the low weight stuff, and you can fix that, and then it's like some tail of some Gaussian that you're not fixing. Okay. And it's like its weight is kind of going to 0 exponentially. Okay. Okay, so I'm waving my hands. You can try and ask me questions, or you can read the notes for the proof. But conceptually, does that kind of make sense? Okay. And I see skeptical looks. But this is getting us the rest of the way towards our goal, right? It's saying I started with this idea started with the ability to design some code, like Shor's code, that corrects just Pauli errors on some number of qubits. And then I've shown that, actually that helps me correct like a realistic noise model, right? So I have some little bit of noise on each of my qubits. And I can see that encoding is going to help, at least if I correct Pauli errors on enough qubits at a time, yeah.
Can you give any intuition for what are things other than Pauli's that can occur?
Yeah, like sort of any channel, right? So the way that you should think about noise is your qubit is going to like couple to some environment. It's going to interact with the environment, but then at the end of the day, you're just interested in the state of your qubit. And so the environment is like your ancilla, and then the interaction is some unitary that mixes them up, and then you like trace out the environment, and then the channel you're left with is your noise. So I don't know, like a very simple example might be like, let's say 1 minus p rho plus px. So, okay, this is still sort of a Pauli thing, but it's just saying I hit it with a Pauli with a certain probability, right? And then I do that to all of my qubits. It's not a single qubit Pauli. Yeah. Yeah.
So just to make sure I understand, the difference between the two theorems is
Yeah.
that the first one we could correct any Pauli errors.
Yeah.
And the second one we just assume that we can correct.
Any errors
I feel like that's
on T qubits.
somehow. Am I missing? Like, I don't know.
So they're building off of each other, right? So this one's saying, or the thought process is, I design a code, it can correct Pauli errors on some number of qubits. Theorem 1 says, oh, actually, that's good enough to get you arbitrary errors on those qubits. And then Theorem 2 says, actually, that's good enough to correct small errors on all of the qubits.
Oh, on all of the qubits.
Yeah.
Okay.
Yeah.
Okay. Cool.
This is
all.
this is acting on all of them.
Yes.
Right.
That makes sense.
Yeah.
Thank you.
Yeah.
Explain the epsilon smaller than or equal to t plus 1 over n minus t minus 1, like where that comes from.
Yeah, I mean, you should, it comes into the proof. Probably wouldn't remember off the top of my head exactly where it comes from, but you should, for instance, like, it's kind of like in the classical case, the analog, right, is like, so remember we said, like I had this first example of the repetition code. Right, and we said, when does this help? Right, each bit is going to get flipped with some probability p, and so here, if I just sent in the logical state directly, I would get the right message out on the other end with probability p. And if I do the encoding first, and then I take a majority vote, what's the probability that, like, I'll only get 1 bit flip error, in which case I'll I'll get back my message correctly. It's going to be, well, okay, so here my probability of failing is p. Here my probability of failing is getting at least 2 bit flip errors. So it was something like p squared, and then there's some combinatorial factor like 3 choose 2 here. And then the code helps if this is smaller than this, right? If the probability of getting 2 errors here was smaller than the probability of getting 1 error here. Okay, so there's some like threshold at which the code starts helping. This is the threshold at which the code starts helping. This is where like the epsilon, i.e. the p, is like small enough that it beats out these combinatorial factors that like blow it up. Yeah.
Thank you.
Yeah. Okay. Okay. So yeah, we can keep going. This is our justification for why, like in the rest of our discussion of error correction, we're just going to be discussing Pauli errors, right? How many qubits can I correct Pauli errors on? Right. When we actually design codes, okay, we'll think more generally in the rest of this lecture, but when we actually go and try and build codes, that's what we're going to try and do. Okay, so the next subject is the second thing. So I said we want to have a more systematic way of understanding which errors are correctable for a given code. And that has to do with what's called the Néel-Laflamme conditions. Okay. So some intuition here. Let's say I have some code space. So like I've mapped my logical space into the physical space, and the image of my logical space is some subspace of the physical space. That's the code space. Let me just suppose this is a two-dimensional code space. So there's these two vectors that would be like the image of, this is like logical 0 and logical 1, or okay. This is the logical 0 state recorded into the physical space, right? And then an error is going to happen, right? So some linear operator acts on this space. So it's going to transform these two vectors in some way. We can kind of think of, okay, this was like my subspace C, and now my new subspace will be like A1, C, A1 dagger. One thing that we want, let me kind of contrast this. Okay, so this is good, right? This is bad. Or this is correctable and uncorrectable, right? So one thing that we want is that when I act with these errors, the orthogonality of my code words gets preserved, right? So the bad picture would be I do A1, and now I have something like this for these two states. And why is that bad? Well, for my error to be like reversible, it better sort of preserve the information that I had, right? So here it's like I can perfectly distinguish the two states. So if I encode it a 0 or I encode it a 1, I can find out exactly after the error happens if I had a 0 or a 1. Maybe they've been rotated or something, but that inner product isn't changed. So they're still distinct states. But here, if the inner product gets messed up, then I know I can't go back, right? I can't, I've lost information there. I'm never going to go backwards. Okay, so that's bad. We want to preserve, something we want is we want to preserve the inner product. Another thing that we want, this is harder to draw, but let's think about, I have another error. Let's call it A2. There's something about how these should fit together or be compatible as well, which is that like, if I do A2 and this just takes me to another subspace of the physical space, and it's totally orthogonal with this one, right? There's like no overlap between the vectors in here and the vectors in here. That's good, because then I can measure, right? I can do some projective measurement that says, that asks like, am I in this subspace or am I in that subspace, right? That measurement will succeed and will tell me like one or the other. And then I'll know like which error happened, right? And so if I need to, rotate these in some way to get back to here, if that rotation is like different whether I'm here or here, I'm okay because I can tell whether I'm here or here, right? So there's like another thing I want, which is like orthogonal spaces, or like images under these errors. Okay, and the other version of that might be like, maybe I have this third error, A3, and one of them takes me to, something like this, and then like A2 takes me here, but then A3 takes me to the same subspace, but with the role of 0 and 1 interchanged. Right. So then if the error happens, I don't know which error happens, and I look here and I see that I'm in like this vector. I don't know if that came from the input being 0 or the input being 1. I've lost that information. Right. Okay, so this is also bad. Okay. Okay, so those are the intuitions of like, what are the conditions that I should have for my error to be correctable? I should be in this situation and not in that one. And now we want to like write that down in math. Yeah.
When you say orthogonal spaces, I should be imagining like these arrows sort of coming out of the board, right?
Yeah, that's why I said I couldn't draw it. Like, yeah, these are.
Yeah, just
There's some higher dimensional space, like the physical space is higher than 2-dimensional, and I just mapped into a totally different subspace.
that makes sense.
Yeah.
But it doesn't matter whether like we're completely out of the original C subspace. Like if we're fully orthogonal to it, isn't that also cool?
Yeah, that's fine. Like, so for example, think of our like very naive like X basis repetition code. So I just wrote down this thing where I take the 0 ket to the 0, 0, 0, and the 1 ket to the 1, 1, 1. The single qubit X errors were correctable. And the original subspace that I start in before any error is the span here, right? And then if I have like a X1 error, now I'm in the span here. And if I have an X2 error, I'm in here. And this is a totally different subspace than this one. Like everything's orthogonal. That's totally different than this one. That wasn't really important. Like for instance, there's another like thing that could happen, which is nothing. I could have the identity, and then I'm in the original space. These are the same. That's fine. But the point is, I'm then going to do that measurement I described, which is like a projector onto the sum of these, or onto this, or the span onto the span of these. And the point is that those were orthogonal spaces. Yeah. Okay, good. So let's be more formal. I have two states, psi and phi, in the code space, which is some subspace of the physical space. It's the image of the encoding. And what these conditions amount to is the statement that I better have the following. Sci-fi. Okay, so why do I want that? Why does that capture my intuitions? Well, let's first of all think of the case where I equals j, right? So remember these things don't have to be unitary. So this can do something, but it's going to map. Like I'll think about it this way. So this is an I right now, and this way. So this is saying, okay, error I happens to phi, and error I happens to psi. So it's like I'm following the same error here, like A1 is happening to both, and I'm going into this same like subspace up here. But then what this condition is saying is that my inner product gets preserved. Right. Okay, so that's enforcing that. And then there's this condition about how different errors fit together, and that the images under the two errors should be orthogonal subspaces. And so now if I is not equal to j, then we're getting a delta here, and this is 0. And so it's saying that this is just a totally orthogonal vector to this. And so indeed, under two different errors, I'm just going into totally non-overlapping subspaces. Okay.
Alex?
Yeah.
Quick question. If we think about like the Shor code, for example,
Yeah.
Z1 and Z2, don't they map the code words into the same space?
Yes. Yeah. So they actually act on the state completely the same way.
Into this picture.
Yeah. So far, I have not said that this condition is necessary. I have said I'm sort of claiming it's sufficient. And in fact, we're going to have to relax this to make it necessary. And yeah, the rest of the discussion is going to be understanding how can I relax this and still correct the errors. So yeah, it's a good point. You're anticipating my sort of next punchline. Okay, so I just want to, I've sort of given this away, but I just want you to think through it for yourself just for a minute. So I just want you to think about this condition in the context of this little repetition code, right? And just write things down and get familiar with the notation here. Why is this holding for the repetition code? Okay, and I just said it wasn't necessary, but it happens to be to happen for that repetition code. Happens to be true, I should say.
I guess this is a condition that has to hold for all code words or all errors. Think of the condition on the left-hand side as weak contractions. Makes sense that we can't get from one code word to another flipping just 2 bits. So whatever I is not true. Satisfies this condition. Now think about the visual space. I'm cooking right now. Bro, you're cooking. Oh wait, is this next? Think about it. This is what you want to reciprocate. You can turn these around. If you spend some time. This progress is like stuck here. It's like it's getting stuck somewhere. I don't really know where. Yes, once he did something. Just it's running this. Yeah, it's running this.
It's not necessarily.
No, that's no. You think hopefully it stunts.
Like it could be XI. Because the repetition will be
Logical space can be thought of as a ground state. Sound for some time. Some expectations. Is the ground subspace accurate? These conditions. Wait, this is so second. You just decide the more.
It's just an object. It doesn't matter.
But you should really put that on AJ because it's almost like he creates.
Yeah.
Just change it to side, yeah, AJ Dagger. Do I look like a... No, but like, totally. What's going on over there?
Okay, so let me say something there.
It's already...
So yeah, in this case, the errors are like, possible errors are x1, x2, x3, and we can think about the identity as well. We can first of all notice that if I equals j, i.e. like I hit them both with an x1 or an x2, then they just cancel out. I get an x to xx, which is 1. And then so clearly, this inner product is preserved. And then if they're distinct, it's actually what I just erased. So, if they're distinct, then like this vector is going to have support in, the subspace where the first bit is flipped. This one's going to have support in the subspace where the second one is flipped, and those are never going to overlap, and then the whole thing is 0. Okay. Okay, but it's good to play with a little bit. Okay, but yeah, as was anticipated, this is not a necessary condition, so we can try and think about how we can relax this further. And one thing we can observe is that let's suppose I have a code that corrects like AI and AJ, right? Then what if let's say AI and AJ are errors that satisfy this condition in particular, right? Then what if I consider a state that's had this happen to it, right? This is a new linear operator. You can think about that. It hits psi. What's that do in this picture? Well, it's like, I started with the code space. Let's think about the case where AI and AJ are mapping you into these, so in this case, these map you into these two orthogonal subspaces, right? So I end up with a state that is a superposition of something in here and something in here, right? Then what my error correction procedure is going to look like is I measure these projectors that like tell me which of these subspaces I'm in, right? So when I just went into one of them at a time, that measurement didn't change the state at all. It just like told me which subspace I went into. Now it's going to collapse that superposition, right? So it is going to change the state, and you're going to end up in one of the subspaces. But it will turn out that, that post-measurement state, once you've collapsed, still preserves the inner product of the original thing, and so it's still recoverable. All the information is still there. It's just instead of being, in one of these two spaces, I've fallen into one of them. Okay, and then I just use that measurement outcome. I say, oh, this is the error that happened, and then I correct that. Right. Okay, so it turns out linear combinations of errors satisfying this condition are also okay. So that means that if I have this situation, I could take, I could define new operators in terms of any sum over the old ones. And this is also okay, right? Okay, and then what does the condition look like now on the B's? Well, I could stick the B's into here, right? And I'm going to get, so I want to compute, like, is there some analogous condition on the B's? Like, so what is this? What should this thing be equal to if the B's are equal to something like this, where the A's satisfy that? I go and compute, so I would get two sums. I'd have like a sum over I and J and a M star L I M K J, and then psi A I dagger A J phi, right? Delta I J psi phi. So this is equal to use the delta, I got one sum. I have ML star I MK I psi phi.
The sum is over LK, right?
The sum is not over LK. So, sorry. Oh, yeah, okay. It should have been, but now I'm going to make myself right. Yeah, so it's there. Okay. What is this? Actually, you can see that this matrix is Hermitian from its form. And turns out any Hermitian alpha, or any Hermitian matrix can be written this way. And so the general form here is just that this thing should be equal to some arbitrary Hermitian matrix times the inner product. Okay. And so that is our more general condition. We can see that that's also fine. And then the theorem from Nil and Laflamme is just that this is actually not just sufficient, but actually necessary. So whenever you have a correctable set of errors, B, L, they'll always satisfy psi, B, L, dagger, BK, phi, okay. Okay. So I've argued, I haven't really proven, but I've argued for the sufficiency of this condition. And then the claim that I'm not proving is that, or not fully arguing for, is that this is actually also necessary. Okay. A proof is sketched in the notes, but it's not fully there. And if you want the full proof, you got to look at Nielsen and Schwang or something. Slightly gory. Okay, questions there?
So, maybe a stupid question. So, is that equivalent to saying that BL dagger BK as an operator Hermitian? Or no?
I don't think so. I mean,
Well, not necessarily.
I think, for instance, that would not capture this part of the constraint.
I see.
Yeah. Okay, so yeah, this part's a bit more technical, and you might need to dwell on it a little bit. But feel free to ask me about it, and can take a bit to digest. But that's my intro. Keep going in the last 10 minutes here to the next lecture. Which is about something called the stabilizer formalism. So we're going to take a little bit of a diversion from quantum error correction. We'll talk about this. We're doing this now because stabilizer formalism that I'm going to describe is a key tool in the design of error correcting codes. So we're going to learn about this formalism, and then we're going to come back next lecture, or in lecture 9, to use this to build interesting codes. Shor's code, for instance, I didn't present it this way, but Shor's code, for example, is an example of a stabilizer code, or code constructed this way. But okay, let's put codes aside for a second, and let me try and explain this. So part of the motivation here is that if we're thinking about Hilbert space, in general, states in a Hilbert space are super hard to describe, right? There can be, if I have n qubits, there's like 2 to the n complex numbers needed to describe a general state in the Hilbert space. And that's kind of awkward or hard to work with. And it's nice to have at least subsets of states or families of states that are sort of easy to describe, but still have kind of rich, interesting quantum-like behavior. So some states that are easy to describe might be something like product states. So if I had a state in an n qubit Hilbert space, which looked like psi1, tensor psi2, psi3, so on, everything's just tensor product, then there, I only need actually 2n complex coefficients to describe this thing. But it's kind of a boring state. There's no entanglement in this state, for instance. And if we want to do error correction, actually, it turns out we need very entangled states. So we're never going to make good codes if we do something like this. Okay, so we need some other way to describe, efficiently describe states that allows for entanglement in particular. And it turns out that the key idea here is to kind of flip our perspective from describing the states directly to thinking of a list of operators that have the state I'm interested in as an eigenvector of that operator. Okay. So we're going to think of, instead of thinking directly about states, we're going to think about operators such that this is true. Okay. And the idea is going to be that if I give you a bunch of operators that all have this state as a +1 eigenvector, it's, if we kind of set up enough constraints, going to describe the state for me. Okay? You can think of this a little bit as like, this is kind of like the Schrodinger versus Heisenberg picture of quantum mechanics. This is like Heisenberg picture of Heisenberg way of thinking about quantum information. We're going to think about the operators instead of the states. Okay, it's going to turn out to add a lot of useful, interesting structure. If we take our set of states that all stabilize, or sorry, my set of operators that all stabilize my state, to not just be a set, but to actually be a group. Okay. And in particular, we're going to think about subgroups of the Pauli group. Okay. So what is the Pauli group? So the Pauli group on n qubits, we'll call it Gn, is just, it's like all strings like tensored together of Pauli operators, identity x, y, and z. And then I have to allow overall phases of ±1 and plus and minus I. Okay. So, examples of elements of, say, the 2-qubit polygroup would be, XX or I, XZ, or something. Okay. Why do I need the plus and minus 1 phases? Well, that's just because I want this thing to be closed. Or sorry, I should say the group operation is multiplication, matrix multiplication of these elements, right? And then if I want to be closed under multiplication, and I have x and z in there, I better have the minus 1 overall phase as well, because x, z, xz, all on the first qubit, that's in my group, and that's just minus 1, right? Because these all anti-commute. And then similarly, I have these y operators, and then I end up being able to make an I or a minus I out of y's. Like a I is like I think it's like a x, I don't know, x, y, z is up to a sign equal to I. Okay, okay, so I have to include the phases. Okay, so we're going to specify states. So in the stabilizer formalism, we describe a special family of states called stabilizer states. And they're going to be described by specifying a subgroup of Gn. Okay. Not every subgroup is going to be a good group for describing a state, but we're going to develop an understanding of when this makes sense. Okay, so very simple examples of stabilizer states. Let's say, I have the state 0. I can either write that down as a cat, or I can say this is the state stabilized by the subgroup of Gn generated by Z, right? If I hit Z on 0, I get 0. This is a subgroup because I could take Z squared, and that's the identity, which also stabilizes 0. Yeah, okay. If I had the plus state, that would be the stabilizer state described by this subgroup generated by X. Okay.
Alex,
Yep.
just a dumb question, but the stabilizer, we allow it to have an eigenvalue, or just it has to be exactly the same state?
Has to be the same state.
So
Yep.
for minus, it's not x, it's minus x.
Yep, that's right. So minus X. Because minus X acting on, minus X acting on minus. This is okay. Okay, so those are very simple single qubit examples. Maybe a more interesting example is like if I have the Bell state, right? What's my stabilizer group now? It's this. Why is that? Well, if I hit this thing with XX, right? Okay, so I should say when you're doing stabilizers, you usually drop the tensor factors and drop the labels on the x's, or sometimes you drop the labels. So if I write XX, it means like x in the first place, x in the second place, not the product XX, so it's confusing. I'll try and keep the labels on. It'd be less confusing, but okay. But yeah, so if I act with x1, x2, flips this to a 1, 1, flips this to a 0, 0, that's the same state, stabilized. And if I hit it with a z1, z2, it does nothing here. It gives me 2 minus signs here, so it does nothing. And so this thing is stabilized. Right. Okay. Okay, so those are just like initial examples. Okay, so I'll leave you with some food for thought. So a claim, sort of simple claim. The set of all the elements like elements in Gn that stabilize some state form a group. Okay, so you can check that if like element 1 acts on psi and gives you psi, and element 2 acts on psi to give you psi, then the product of those is also going to give you psi. Yeah.
When we describe this stabilized states and subgroups, do we have to take like a maximal subgroup of Gn? Because I could have taken just x1, x2, for example, for Bell state.
So here I'm taking the group generated by x1, x2. That actually turns out to be maximal. Like that generates everything that stabilizes this. But yeah, I was kind of being just sort of quick and informal here, and then we're gonna like carefully say like, you know, why am I taking a group? How big should this thing be to specify like a state? Like if I had just done this, I wouldn't have specified the state fully. I needed 2 elements. Why did I need 2 elements? So we're gonna get into all that in the next lecture. Yeah. When do I know I have enough elements? Like you're asking. Yeah. But okay, that's it for now. Sorry to go over a little bit, and I'll see you in tutorial tonight, I think. Yeah, or later today.